This is SpaceTime Series 25, Episode 1, for broadcast on the 3rd of January 2022. Coming up on SpaceTime, the biggest scientific discovery of the past year, the detection of a huge new population of free-floating planets, and China ends 2021 with a flurry of rocket launches. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
One of the unquestionable highlights of the past year in scientific research was the historic confirmation that one of the densest objects in the universe, a neutron star, has been consumed by a black hole, the only thing in the universe that's even denser. The discovery, using gravitational wave observatories across the world, provided unquestionable proof of a long-held hypothesis. Finding one black hole neutron star merger was spectacular enough, but detecting two such events just 10 days apart in different galaxies was absolutely stunning. The observations, reported in the Astrophysical Journal Letters back in June, were based on readings gathered some 18 months earlier at the start of 2020. It took some 900 million years for the gravitational waves from these massive collisions to reach the Earth. The findings will enable researchers to draw their first conclusions about the origins of these rare binary systems and how often they merge. Gravitational waves have previously allowed scientists to detect mergers between pairs of black holes and pairs of neutron stars. But the long-held hypothesized merger of a black hole with a neutron star has always been an elusive missing piece of the family picture, at least until now. Neutron stars are super-dense stellar objects, created out of the supernova explosion of some of the universe's biggest stars. And stellar mass black holes are created when even bigger stars go supernova, collapsing down into objects so dense that nothing, not even light, can escape. Put simply, a black hole is an object of infinite density in zero volume. With these three detections, astronomers finally have measurements of the merger rates across all three categories of compact binaries: black hole with black hole, neutron star with neutron star, and black hole with neutron star. The research was a joint collaboration between the LIGO Laser Interferometer Gravitational Wave Observatory Scientific Collaboration, the Virgo Collaboration, and the new Japanese Kamioka Gravitational Wave Detector, or KAGRA project. The physicists observed the two gravitational wave events, catalogued as GW 2001-05 and 2001-15, on January 5, 2020 and January 15, 2020, during the second half of the LIGO and Virgo detectors' third observational run. Although multiple observatories carried out numerous follow-up observations, none observed light from either event. But that's not unexpected. In fact, it's consistent with both the measured masses and the distances. The new discoveries follow earlier tantalizing observations of a black hole merger with a mystery object which may well have been an extremely massive neutron star. But it could also have been a really lightweight black hole. Scientists were never sure. So the search continued. Both the LIGO and Virgo observatories detected GW 2001-15, which resulted from the merger of a 6 solar mass black hole with a 1.5 solar mass neutron star, roughly 1 billion light-years away. Using data from the observations of these three widely spaced detectors, scientists were able to determine the direction of the wave's origin. Just 10 days earlier, the Virgo detector and one of the LIGO detectors observed a strong signal from GW 2001-05. That signal was caused by a 9 solar mass black hole colliding with a 1.9 solar mass compact object, which scientists ultimately concluded was a neutron star. That merger happened at a distance of about 900 million light-years, but the signal was only strong in one of the detectors, so astronomers couldn't determine its precise origin. Still, because the two events are the first confident observations of gravitational waves coming from the merging of black holes with neutron stars, astronomers can now estimate how often such events are likely to happen across the universe, suggesting there's possibly one such merger per month within a distance of 1 billion light-years. One of the study's authors, distinguished Professor Susan Scott from the Australian National University, says while it's unclear how or where these binary systems originate, astronomers identified three likely cosmic origins: stellar binary systems, dense stellar environments including young star clusters, and the centres of galaxies.
Well, we were very, very excited to get these two events because they're actually the first ever observation of a binary system of a black hole and a neutron star, and they're spiraling around together and colliding. So we've collected the gravitational waves from this type of event for the first ever time. So it's amazing to finally confirm the existence of these systems and to get a bit of a look at it.
So what do we know about these two systems?
Well, the thing about these detections is that we were able to put the secondary object, so you have the primary is the bigger one. Primary one falls squarely into the range of black hole masses, so we can definitively attribute it to being a black hole. And for these two events, the lighter one falls well into the range of normal neutron star ranges evidenced by neutron stars in our own galaxy. So there was no kind of ambiguity about the type of objects involved. You may recall that in August 2019, we thought we may have seen such a system, but the lighter object was above the heaviest known neutron star, so it made it very ambiguous. I mean, was it the heaviest ever neutron star, or was it in fact the lightest ever black hole? And to this day, we don't know, of course. And the other event we had was earlier that year in April 2019. We had another signal which we thought could be such a system, but the signal was quite ambiguous in the sense that it was weak and, possibly could have been due to detector noise.
So this time there's no doubting it. It's definitely a neutron star merging with a black hole, and we haven't just seen one of them, we saw two of them.
Yeah, we saw two of them 10 days apart on the 5th and 15th of January last year. So, after waiting more than 4 years since our first detection of gravitational waves from two black holes colliding, we've had quite a long wait for the third part of the puzzle. We were very excited to have it, but we do think that when we start up again next year, middle of 2022, with a bit more sensitivity, that we could be detecting as many as one of these type of events per month out to about 1 billion light year distance.
And the work being done now on the LIGO detectors, what does that involve?
We're trying to improve aspects of the squeezing, which is something that we introduced before the last observing run, so that always has room for improvement. But also these instruments are getting quite aged by now, so they have maintenance and things to do to maintain the purity of the beams as much as possible within the vacuum tubes and things of that nature. And we're always looking to improve isolation from worldly vibrations, so the various things due to people making noise, driving trucks, aeroplanes, seismic waves, that sort of thing. So we're always trying to improve that end of it as well.
Now, with these particular detections, we join a new observatory to the team. The Kamioka Observatory has come on board. Yes,
the Japanese experiment and detector did join during the third observing run for LIGO and Virgo, and they weren't obviously at great sensitivity, because when you start up interferometric ground-based detector projects, it takes a long time to crank up the sensitivity. I mean, with LIGO, it took us several years to really keep improving, and we're still doing it, as you know. But it means that obviously LIGO is a bit ahead of Virgo, and Virgo is ahead of CAGRA, and so on. And therefore, we come into each observing run with different sensitivities, and this does have some impact on what we do. You get a stronger signal in the two LIGO instruments and a weaker one in Virgo. It's still very important because we can get directionality, get a smaller chunk of the sky to give to astronomers to follow up and things like that, but also it can contribute to aspects of the signal analysis as well.
And CAGRA, this is an underground detector as well, isn't it?
That's right. CAGRA is based under Kamioka Mountain, so it's under 1,000 metres of granite. And I think the thinking there with the Japanese design team was that it would help to damp seismic activity, because as you know, Japan is very seismically active, and so to have it under 1,000 metres of granite definitely helped in that regard. But the other thing they're doing, which has not been done yet on the other detectors, is it's cryogenic. So they're introducing, significant cooling to the instrument to help eventually improve sensitivity.
Now, this marks more than 50 detections. That's pretty cool.
It is pretty cool. And, the remarkable thing about all this is they're not just detections. That every time we get one of these sort of detections, it adds to our information about, for example, the rate at which these types of systems are merging in the universe. So the rate of two black holes merging or two neutron stars or one of each. And that in turn gives us information about the occurrence of such systems and indeed such objects throughout the universe, but also by studying parameters of the collision, looking at the masses and spins of the objects involved, we can refine our theories about how these systems get together in the first place. For example, the current ones, a neutron star and black hole, could this system possibly have formed in the very dense centre of a galaxy and the two objects were kind of thrust together at some point, forming a binary, or indeed at the centre of a globular cluster? Or did they perhaps form really in relative isolation and formed as two giant stars and then eventually went through their life cycles, alternately going supernova and then collapsing, one to form a black hole and one to form a neutron star? So we do look at the information we get from these systems to formulate theories about the main ways these systems are being formed throughout the universe.
And any conclusions as yet with the samples you've now got?
It was interesting. The second one, the primary object, the bigger one, the black hole, seemed to have its spin in the opposite direction to the angular momentum of the binary system. And that can suggest that this was a product of being kind of thrust together in a very dense environment. Whereas with the two objects with their spin much more closely aligned, that might well suggest developing in a more isolated environment, for example.
Now, there weren't any electromagnetic readings with these collisions, were there?
No, and there's a couple of reasons for that. Is the first collision, LIGO Hanford, was down, meaning it didn't collect data. So we only had two instruments, and that always gives a bigger region of sky to give to the astronomers. The other thing is that we think these two particular collisions, that the smaller object, the neutron star, was probably more or less swallowed whole by the black hole as it got to the event horizon. And when that happens, of course, it doesn't give off much of an electromagnetic signal. Whereas we can imagine other situations, depending on the relative masses, if they're much closer together, depending on the spin orientations as they get together and their velocities and also the environments where they're formed, it may be possible in certain circumstances like that to get a signature, a flash shredding of the neutron star through tidal deformation. So the black hole kind of pulls the neutron star slowly and shreds it and creates this very hot debris close to the black hole, which could give a signal for powerful telescopes if the event is reasonably close.
Yeah, that's always one of the fears involving black holes, that they're acting too quickly to leave any remnant crumbs lying around to be seen in electromagnetic detectors.
Yes. Well, when we have two black holes coming together, of course, we don't expect anything. But we do know through the two neutron star first collision we had in 2017 that was readily observable, actually, with light, radio.
Yeah, the first ones,
yeah, the very first one. We actually got a really good look at it, and that's how we got so much information out of it, like the synthesis of heavy elements and so on, and the gamma ray burst associated with it. And we got a lot out of that. So we know we can get a lot of information, particularly from binary neutron star systems. But we also believe there's potential for black hole neutron star mergers if they're close enough and if the parameters of the system are in the right kind of regime to make a shredding happen.
That's Professor Susan Scott from the Australian National University. And this is SpaceTime. Still to come, discovery of a huge new population of free-floating planets, and Iran continues its nuclear weapons campaign with another rocket launch. All that and more still to come on SpaceTime. Astronomers have discovered at least 70 free-floating planets, that is worlds not orbiting stars, in our part of the galaxy. The findings, reported in the journal Nature Astronomy, almost doubles the number of free-floating or rogue planets known to exist. The first free-floating planets were discovered back in the 1990s. These new discoveries were identified in a nearby region of the Milky Way known as the Upper Scorpius OB Stellar Association, located some 420 light-years away, relatively close in astronomical terms. The region contains a number of famous nebulae, including the Rho-Ophiuchi Cloud, the Pipe Nebula, Barnard 68, and the Coalsack. At least 70, and possibly as many as 170 of these Jupiter-sized planets have been found in the data, which is based on more than 20 years of observations. The range and number of free-floating planets occurs because the mass of the objects has not been measured directly in the study. See, objects larger than 13 Jupiter masses are not likely to be planets but brown dwarfs. And an upper limit on the mass of these objects was inferred by the object's brightness, and that's dependent on their age. Now, since spectral type O and B stars are known to have very short main sequence lifespans, usually lasting just a few million years, the exact numbers of planets is uncertain. Until now, free-floating planets have mostly been discovered through microlensing surveys. These involve astronomers seeing a brief chance alignment between an exoplanet and a background star. However, microlensing events only happen once. That means follow-up observations simply aren't possible. These new planets were discovered using a different method. The planets, lurking far away from any star illuminating them, would normally be impossible to image. However, astronomers took advantage of the fact that these planets are still very young, just a few million years old at most, and so they're still hot enough to glow, making them directly detectable using sensitive cameras on large telescopes. So the planets were found using multiple large observatories, including the European Southern Observatory, the Canada-France-Hawaii Telescope, the Subaru Telescope, the Kitt Peak National Observatory in Arizona, the Cerro Tololo Inter-American Observatory in Chile, and the Dark Energy Camera. This amounted to some 80,000 wide-field images over 20 years of observations and archival data in both optical and near-infrared. The discovery also sheds a light on the possible origin of free-floating planets. Some scientists believe that these planets can form from the collapse of a gas cloud that's simply too small to lead to the formation of a star. Others believe that they've simply been flung out from their parent star system by gravitational perturbations. Our own solar system is thought to have had an additional planet which formed somewhere between Uranus and Neptune, but was flung out by gravitational perturbations as the gas giants Jupiter and Saturn migrated in towards the Sun and then back out again. And the ejection model suggests there could be even greater numbers of free-floating planets that are smaller, more Earth-sized. Free-floating Jupiter-mass planets are the most difficult to eject, meaning there might be a lot more super-Earths or even Earth-sized worlds wandering out there in the galaxy, alone in the dark. This is SpaceTime. Still to come, Iran launches another rocket as it continues its nuclear weapons campaign, and a Dragon cargo ship docks with the International Space Station carrying 3 tons of fresh supplies. All that and more still to come on SpaceTime. Iran has moved a step closer to developing a nuclear weapon and the means to deliver it with the launch of another missile and what military experts are describing as a thinly disguised rocket launch. The launch took place amid ongoing talks in Vienna about the Islamic Republic's repeated breaches of its 2015 nuclear non-proliferation agreement. New Iranian demands in the nuclear talks have exasperated Western nations and heightened regional tensions. Iran has abandoned all limitations under the agreement, both increasing its uranium stockpile and dramatically ramping up uranium enrichment. This latest launch took place from the Imam Khomeini spaceport some 240 kilometers southeast of Tehran. The Iranian Defense Ministry says the Seymour rocket carried 3 devices to an altitude of 470 kilometers and a velocity of 7.35 kilometers per second. Now, that's far too slow to achieve orbit. And that's raised concerns about whether this was an unsuccessful orbital launch attempt or a successful suborbital test flight. Tehran officials have remained silent on the status of the mission. That suggests the rocket failed to place its payload into orbit, and follow-up observations have also failed to find any trace of these 3 payloads being in orbit. The US State Department says it remains concerned by Tehran's actions, which pose a significant proliferation concern in regards to Tehran's ballistic missile program. Meanwhile, Germany says the launch has violated UN Security Council resolutions. The Simor, or Phoenix, is a three-stage missile based on the North Korean Un-Ha missile, which itself was developed out of a Russian Scud missile. Its first stage uses a cluster of 4 Shahab-3 missile engines. The Shahab-3 is based on the North Korean No-Dong. The Simor's second stage uses a low-thrust steering engine that's a Vernier engine used by the now obsolete Soviet R-27 submarine-launched ballistic missile. There have been at least 4 previous Simor launches, all of them failures. The first was in July 2017, that was followed by one in January 2019, another in February 2020, and finally one in January last year. This is SpaceTime. Still to come, a new Dragon docks with the International Space Station, and China ends 2021 with a flurry of orbital missions. All that and more still to come on SpaceTime. SpaceX's CRS-24 Dragon cargo ship has successfully docked with the International Space Station 418 kilometres over the South Pacific Ocean. The Dragon, carrying almost 3 tons of supplies, scientific equipment and experiments, docked automatically with a space-facing port on the orbiting outpost Harmony module as the 2 spacecraft were travelling at over 28,000 kilometres per hour. The Dragon had launched the previous day from Space Launch Complex 39A at the Kennedy Space Center in Florida.
Stage 2 locks throttle back. Stage 2 locks load complete.
The vehicles.
Dragon is in auto idle. Falcon 9's in startup. Dragon is in countdown.
Falcon 9, CRS-24, go for launch.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ignition.
Liftoff. Cargo Dragon soars with the final supply run in 2021 for the astronauts aboard the International Space Station.
Stage 1 chamber pressure is nominal.
Falcon 9 and Dragon
Power
have
telemetry nominal.
passing through the cloud layers right now. Next up, in just a few seconds here, is Max Q. This is where the vehicle will experience the highest amount of aerodynamic pressures.
Falcon 9 is supersonic. Max Q.
Through that period of high pressure on the vehicle, the engines on the first stage are now throttling back up as we continue to make our journey to orbit. Coming up in about a minute are 3 events in rapid succession. First up is main engine cutoff, also known as MECO,
Engine chill
followed by
started.
stage separation, and then second engine start, also known as SES-1. Main engine cutoff is where all 9 engines on the first stage will shut off in preparation for the second event, stage separation. During stage separation, the first and second stages will separate from one another. The first stage makes its way back to the drone ship for a landing attempt, and the second stage will ignite its Merlin vacuum engine and continue to boost Dragon to low Earth orbit.
MECO. Stage separation confirmed. INVAC ignition.
You heard the call-outs. Successful main engine cutoff, followed by successful stage separation, and then ignition of our Merlin vacuum engine. The first stage, again, it's making its way back to Earth, the 24th commercial resupply mission to the International Space Station for NASA. This is SpaceX's 31st mission for 2021 and the 5th Dragon flight to the International Space Station this year. Our hypersonic grid fins, they're positioned at the top of the first stage booster. There are 4 of them, actually, and those will start to swivel and move around to make sure that they are guiding the first stage back to its targeted landing zone. For today's mission, it's going to be the drone ship Just Read the Instruction, which is parked in the Atlantic Ocean. Next event for our mission today is going to be the first stage entry burn. It's going to be the first of 2 burns. In order to make its way back to our drone ship, the first stage has to execute these 2 burns. The first, again, is the entry burn, where 3 of our Merlin engines will reignite. This helps to slow the stage down as it re-enters enters the upper parts of the Earth's atmosphere. The second burn is the landing burn. This happens about a minute later. This is a single engine burn that will bring the vehicle speed down rapidly in order to land on the drone ship. And as we wait for that event, you might be interested to know that in order to get into space, the rocket actually has to do more than go up. It actually has to go sideways really, really fast. At liftoff, gravity is pulling straight down on the rocket, and as we ascend, we tilt the engines, a term called gimbaling, and that turns the rocket horizontally. So we're still going up, but we're also heading horizontally away from the launch pad in what we call a gravity turn.
Stage 1 FTS is safe.
Things continue to go smoothly for both the first and second stages.
Stage 1 entry burn is in startup.
And there it is. 3 Merlin engines have reignited their engines and are now currently slowing down the first stage. This burn is expected to last about 30 seconds. The velocity is starting to decrease significantly.
Stage 1 entry burn shutdown.
So great news. That is burn 1 of 2 complete. The Falcon 9 first stage is also equipped with 4 landing legs made of state-of-the-art carbon fiber with aluminum honeycomb. They're placed around the base of the rocket and deployed just prior to landing. So we are about 60 seconds away from landing the vehicle. We're traveling a significant velocity right now, and this really puts into perspective the deceleration that the first stage will experience. In less than the span of a minute, we'll reduce from twice the speed of a jet all the way down to 0 as the rocket lands.
Stage 1 is transonic.
The first stage landing burn is expected to start here in about 20 seconds and last for about 25 seconds. So during the duration of that burn, we are going to be listening for the call out for SECO, which stands for second engine cutoff. The Merlin vacuum engine, we're going to be shutting off that engine and then listening for another call out for a confirmation of good orbit,
stage
where the second stage will coast for a few minutes before separating Dragon.
Stage 2 FTS is safe.
And the landing burn
Stage 1
is
landing
currently underway.
INVAC shutdown. Stage 1 landing is confirmed.
There it is. So this is the first landing for this particular booster, but the 100th successful landing for an orbital class rocket. What a way to end off the year. We also heard that the the second stage engine, the Merlin vacuum engine, successfully shut off its engine. And we're going to pause here to see if we can confirm a good orbit of the second stage.
Expected loss of signal, Cape. Acquisition signal, Newfoundland.
And I am getting confirmation that we do indeed have a good orbit. So the second stage is going to be coasting for a few minutes here. The second stage right now is making some small adjustments during the coast phase prior to separation. Dragon is going to be joining the Crew 3 vehicle Endurance that is currently attached to the International Space Station and on orbit. And as always, it's always exciting to see 2 Dragons docked at the space station at the same time. And speaking of cargo, today we'll be delivering as part of today's mission, we'll be delivering more than 6,500 pounds of science, research, crew supplies, and vehicle hardware to the orbiting lab and its crew. Again, this is a cargo mission, so there is no crew aboard the Dragon as part of today's mission. And in fact, we will modify the vehicles slightly for these types of missions. So there are no seats, there are no life support systems. This saves weight. It also frees up some space for more cargo, and it also allows us to refurbish the Dragon a little bit quicker once it splashes back down to Earth in about a month.
Expected loss of signal, Bermuda.
Stage separation confirmed.
Any second
Dragon
now.
separation.
And there it goes. The Dragon has about a day before it makes its way to the International Space Station and docks.
The mission carried 386 kilograms of crew supplies, including Christmas gifts, 182 kilograms of spacewalking equipment, 328 kilograms of space station hardware, 33 kilograms of computer equipment, and 1,119 kilograms of scientific equipment and experiments. These included a new German handheld bioprinter, which uses viable cells and biological molecules to print tissue structures in order to create a tissue-forming patch to cover a wound and accelerate the healing process. Also aboard was a space protein crystal growth experiment. It's designed to improve drug delivery of monoclonal antibodies used to treat cancers and a wide range of other human diseases. There was a study to assess the virulence of potentially harmful microbes in space. That comes after scientists noticed a reduction in astronaut immune function in microgravity. There was a so-called roots, shoots and leaves experiment which looked at the development of plants in microgravity. Other experiments will look at manufacturing alloy turbine blades in space. That comes following the discovery that alloys seem to blend better in microgravity. There was an antibiotic resistance in microgravity experiment, which looks at how microgravity affects bacteria-resistant polymers. But one of the most talked about experiments involves doing the laundry. See, crew on the space station currently wear clothes several times, then replace them with new clothes which are delivered on resupply missions. That's all very expensive. So scientists have developed a study to see how a fully degradable detergent specifically designed for use in space works. It could lead to astronauts doing their own travel wash, a sort of lunar laundromat if you will. The Dragon will spend a month docked to the space station before returning to Earth with hardware and completed experiments. We'll let you know how the laundry experiment works out. This is Space Time. Still to come, China ends 2021 with a flurry of orbital missions, and later in the science report, an ancient synagogue older than Christianity or Islam discovered in Galilee. All that and more still to come on Space Time. China has ended 2021 with a flurry of rocket launches as it continues what Beijing euphemistically describes as preparations for war. The final weeks of the year have seen the launch of a Long March 4C rocket from the Taiyuan Satellite Launch Center in northern China's Jiangxi province, carrying the ZY-102E Phoenix Eye Earth observation satellite. The 2,000-kilogram spacecraft is equipped with high-resolution panchromatic and multispectral images, including a 9-band visible and near-infrared camera and a 166-band hyperspectral camera. The satellite is designed for continuous imaging, high data storage and transmission capabilities, providing 900 megabits per second of data transmission using dual-spot beam antennas and high data storage capacity. It's been placed into a 778-kilometre-high sun-synchronous orbit, joining its sister satellite, the ZY-102D, which was launched in September 2019. A few days earlier saw the launch of a 61-metre-tall Long March 7A rocket from the Wenchang Satellite Launch Center in Henan Province, carrying the Shiyang 1201 and 1202 satellites into geosynchronous transfer orbit. Beijing claims the twin 3,000-kilogram spacecraft are being used for space environment studies and related technical tests, but their exact purpose and payload specifications has remained classified. So, what are they really? Well, intelligence sources suggest they're designed for electronic surveillance and reconnaissance, monitoring the communications and signals intelligence of other countries. Since 2016, Beijing has launched more than 153 Earth observation satellites, designed to provide near-continuous high-resolution imaging and electronic monitoring of areas of interest to China. Beijing's also launched a Long March 3B rocket carrying a new telecommunications relay satellite into orbit. That was launched from the Zhejiang Satellite Launch Center in southwestern China. The Tianlian 1102 is part of China's second generation of space communications relay satellites, designed to improve communications between Beijing and its growing constellation of more than 446 spacecraft, which have included more than 50 launches over the past year. This is Space Time. And time now to take a brief look at some of the other stories making news in science this week with a science report. A new study claims that Moderna's vaccine appears to be slightly more effective at preventing COVID-19 infection and hospitalization. The findings, reported in the New England Journal of Medicine, looked at some 220,000 US veterans who received Pfizer with the same amount who received Moderna and compared the outcomes over 6 months. The researchers say while the incidence of COVID-19 infection in both cohorts was very low, Pfizer recipients had a 27% higher risk of infection and a 70% higher risk of hospitalization compared to Moderna recipients. Almost 5.5 million people have now been killed by the COVID-19 coronavirus since it first spread out of Wuhan, China. However, the World Health Organization says the true death toll is likely to be double that amount, with almost 300 million confirmed cases. New data suggests that the presence of pollutants in the air or water, including lead, mercury and arsenic, may be linked to a changing percentage of baby boys being born compared to baby girls. The study, reported in the journal PLOS Computational Biology, analysed more than 6 million birth records in the United States and Sweden and looked for factors that appeared to be linked to changes in the ratios of boys versus girls. The authors found that seasons, temperatures, violent crime rates, unemployment rates, or commute times all had no link with the sex ratio. But some pollutants did, along with extreme droughts, traffic fatality rates, industrial permits, and vacant apartments in the area. However, the study couldn't determine whether or not the pollutants actually caused the changes in the sex ratio between boys and girls. And the authors say more work is needed. It's been confirmed that the ADF will ditch its troubled European MRH-90 Taipan helicopters and replace them with additional UH-60M Black Hawk and MH-60 Romeo Seahawk helicopters instead. The move follows Canberra's recent decision to replace the Army's current European Tiger attack helicopters with American AH-64E Apache Longbows. And in a classic I told you so moment, our long-time Star Stuff and SpaceTime listeners might recall that we urged the Defense Department to purchase the Apache Longbows rather than the Tigers some 20 years ago. Pity they didn't listen. Oh well, it's only taxpayers' money, isn't it? An ancient synagogue dating back some 2,000 years to the time of the Second Temple in Jerusalem has been discovered by archaeologists in northern Israel. The find, which is older than Christianity and Islam, was discovered at the dig site of Magdala, an ancient fishing town on the western shore of the Sea of Galilee. The city, which was also known as Migdal in Hebrew, is said to be the hometown of Mary Magdalene. The discovery sheds light on the social and religious life of Jews in the Galilee region during this period, and it's the second synagogue to have been uncovered in the village. The first was discovered in 2009. The new discovery includes a large stone portraying the Second Temple of Jerusalem and a carved 7-branch candelabra known as a menorah. There are growing concerns regarding the dangers of alternative allergy tests. Adverse reactions to food are common and estimated to affect around 20% of the population. And while potentially dangerous, they're increasingly being diagnosed using unorthodox and scientifically unsound methods. Tim Mendham from Australian Skeptics says it's not just a case of pseudoscientific rip-off. Severe allergic reactions such as anaphylaxis affecting breathing and the heart can be life-threatening.
A lot of people suffer from food reactions. I say about 20% of people have some sort of reaction. Food allergies about 1%, where you actually come out in all sorts of quite scary sort of conditions. Food intolerance is like where you just don't work well, like, people don't like milk or something or whatever. So, and that's a lot more people suffer from food intolerance. But the thing is that because this is so common and because some of the symptoms are so scary, including potential death in some cases, naturally enough, the alternative scene has come up with a lot of treatments for this and preventions and all sorts of things, and most of them, or at least a lot of them that have come up, are totally bogus entirely. You get, some are based on technology, some are based on analysis or something, some are based on totally silly supposed scientific practices or even physical practices. One of them is, it's called voice bio, which is basically analysing your voice. I'm not quite sure exactly how you analyse your voice, what for, but drawing conclusions based on the sound wave frequencies. You can show what organ dysfunction there might be in the presence of allergies and intolerances, purely from your voice. So if you've got a croaky voice or something, they might show, well, you're allergic to peanuts. It just doesn't work.
It works in relieving you of your money.
It's very effective at doing that, actually. It's highly effective. In fact, probably most of these are highly effective at wallet reduction syndrome. But
I've never heard it called that before. I like that.
I just made it up. It's scientific. Yeah, I think I will actually, but I'm as good as any alternative method I can make up.
Very scientifical.
Yeah, very scientifical, yes. Kinesiology was the one where you're sort of judging by your muscle strength. It's often the case where they do it where someone's got their arms stretched out either side of themselves, and you can push them over at some stages or you can't push them over, and the whole thing is, it's just totally bogus. It depends on the person's preparedness for being pushed over or not being pushed over. It depends on where the person who's pushing you over, pulling down your hand, etc., how that works. Nothing in kinesiology, certainly in applied kinesiology as it's called, but that's supposed to find out about your susceptibility to allergens, etc. Blood samples, of course, hair analysis are other ones. Hair analysis is very poor. There was, or I presume there still are, labs you could send your hair off to for analysis, and it would come back to you with what sort of medical conditions you have. I don't know about why allergens and things crops up, but medical conditions, and people have done tests by sending 2 lots of hair analysis down, the same hair, exactly taken from the same place, etc., sent down under different names, and you get different analyses. So pulse testing is sort of measuring out your pulse rate, etc., and that gives you a diagnosis of if your pulse increases after certain sort of foods, etc., you're obviously allergic to it. And it goes on and on and on. And the trouble is that what these things do is, of course, they, apart from the fact they're unreliable, they can be expensive, they're unregulated, and they might mislead patients into thinking they have an allergy or they don't have an allergy, and that could make them do things which is not necessary. And, of course, it also takes people away from doing proper tests. If they think one of these alternative tests can give them the result, despite how bogus they are, that's where they're dangerous. So they stop being just fun and silly, and they become serious.
That's Tim Mendham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.